Obviously, this tombstone solution can be improved, meaning to say that I'm still going to use some memory leakage in order not to have a dangling pointer. But I'm going to try to minimize the leakage. And the way to do that is to disconnect between the tombstone and the actual heap memory. What does that mean? So if we draw the picture again, so we have some heap memory, and in some other separate location, we have a tombstone. This is our tombstone, right? And when we have some pointer A pointing at the tombstones, which points at the heap memory, and we have some other pointer B pointing at the same tombstone, which points at the memory. Now, suppose, for example, that we actually go and we disconnect A from the tombstone, which means we deleted the heap memory. So this disconnected and this became null. Now, by this becoming null, this also disconnected. And we have this tombstone still sticking around. Now let's go through what would happen if B tries to access the heap, and what would happen if somebody else tries to access this heap memory. So let's start with B. Suppose B tries to access the heap memory. So you have, let's say, star B, which we said already becomes a double star B. And we already know that this is actually just a null pointer dereference. And we have a thrown exception, which is exactly what we want. We want if somebody should access, if this one was a dangling pointer, that's what it was. Right, this was a dangling pointer. So if we actually have this dangling pointer, so we want to know that it's dangling, and by throwing a null pointer exception, so that's okay. We can do a graceful degradation. So that's great. So B will know that it became dangling, and it wouldn't access the actual heap. Now, what would happen if somebody else tries to actually go and actually allocate this heap? So we have here C, just like before, and C wants a new memory. What C would do, it would create a new tombstone and point to the new tombstone. That's what it would do, which would in turn point to the actual new heap, the old heap, I would actually say. Now notice what happened. If C tries to access, so we actually get a double star C, which is perfectly legal, you actually get the value. If at this point in time B tries to access, right, so we do now star B, which would again becomes a double star B, we still have a null pointer exception. So in a sense, by disconnecting the tombstone from the heap, we're actually allowing us to reuse the heap. Notice that this heap right here is being reused. Right, this is reused. And it's actually the same heap that was owned once upon a time by A and B. The tombstone itself is still being leaked. That didn't change. Notice this part right here is being leaked. And if C disconnects from the heap, then this will be leaked separately, right? So every time you allocate new memory, you're actually allocating a tombstone and some memory. And anytime you deallocate the memory, the tombstone stays and the actual heap gets reclaimed. So we are still getting a memory leaked, right? This is still mem leaked, but it is much smaller than before. We're actually only leaking a pointer. That's what we're leaking. Before we leaked as much of the heap that we allocated, and now we're only leaking one pointer per allocation of heap, which must always stay. You can't deallocate the tombstone, else B might try to access the memory that it can't access. You have to somehow have a null pointer exception. So here we have an improved version of the tombstone, which, as I said, is leaking a lot less, one pointer per allocation, but it's still leaking memory, which means it doesn't change the basic premise of what I was talking about, that the engineers or whoever developed this languages that use tombstones actually will go and use memory leaks to solve the problems of of dangling pointers. That's still true, right? But we still are able to figure out a way how to actually make it more efficient. But again, as I said, notice the usage and the offset between dangling pointers and memory leaks.